Section 7.3, sampling distributions and the central limit theorem. And these are the objectives. Tonight you will learn about constructing a sample distribution of a sample mean and use the central limit theorem to compute probabilities involving sample means. Okay, in a real situation, statistical studies involving sampling several individuals, then computing numerical summaries of the samples. So, for example, we usually compute for the mean. So let's say you have a population, and then out of the population, you get a sample, let's say, with a population of 1,000, you get 100. So when you get 100 as a sample, you get the sample mean, right? And let's say another one got a sample again from out of the total population of 1,000. It's for sure it's not going to be the same 100 students, right? So you're going to get a new set of sample with the new sample mean. So if you have a larger population, if you have, and then you get different samples and you get those different means, that is what we're going to do for this section. So if several samples are drawn from a population, they are likely to have different values of mean because of the value of the mean varies each time a sample is drawn. And that mean is a random variable. For each value of the random variable, we can compute a probability, and the probability distribution is called the sampling distribution of mean. So remember before you learn about how to construct probability distributions. So this time we're gonna construct a sampling distribution of all the means. So an example here of a sampling distribution. A tetrahedral dice are shaped like a pyramid, like these two here, with 4 faces. Each phase corresponds to a number between 1 and 4. Tossing a tetrahedral die is like sampling a value from the population and all the possibilities 1, 2, 3, and 4. And we can easily find the population mean. So when you add those numbers, 1 plus 2 plus 3 plus 4, and then divide it by 4, and 4, 7, 8, 9, 10 divided by 4, the mean is equal to 2.5. So that is your population mean, and the population standard deviation is 1.118. Suppose that the tetrahedral die is tossed 3 times. The sequence of the 3 numbers observed by, may be thought of a sample of size 3. There are possibilities when you toss it 3 times, you might get 111, 112, 113, and so on and so forth. And these are all the possibilities actually. So it's possible for you to get 111 up to 444. So those are all the possibilities. And if you get the means of all these possibilities here, where's my, so this is a possibility 111, and if you get the mean of all these 3 numbers is equal to 1. Another possibility is, let's say 2, 3, and 1. If you add all this and divide by 3, you will get the mean of 2.0, or let's say 4, 3, 1. 4 plus 3 plus 1 divided by 3, the mean is 2.67. So all of these means these are all the possibilities. And comparing all this is a lot if you get to compute for the means of all the means, right? So that's why we're gonna have a formula for this. I'm not gonna ask you to compute the means of all the possibilities because that's a lot. And we have a formula here. First, the mean of the sampling distribution is denoted by mu of x bar, meaning the mean of all the means. is always equal to the population mean. Just like if you go back here, these are all the means. If you compute the mean of all these numbers, it's going to be exactly equal to 2.5. So meaning whatever the population mean is, the mean of all the means is equal to that. So that's why we have this formula. And then the standard deviation is, copy this, the standard deviation of all those means is equal to the standard deviation over the square root of your total n. This is harder than computing for the mean, because you're gonna get, instead of getting the standard deviation of 3 ones, 1 1 2, 1 1 3, and so on and so forth, that's a lot. So to compute that, it's just simply standard deviation over square root of n. So make sure that you copy those two formulas. And we're going to need to use this to solve for the probabilities, the normal distribution. Remember, this chapter is all about the standard normal distribution. So meaning we're still going to use normal CDF here. And remember our normal CDF, you use a lower, upper, mean, and standard deviation. So this is going to be what we're going to use here. This is going to be your mean, and this is your standard deviation. Any questions? All right, an example here. Among students at a certain college, the mean number of hours of television watched per week is 10.5, and the standard deviation is 3.6. A simple random sample of 16 students is chosen for a study of viewing habits. Let X bar be the mean number of hours of TV watched by sample students, and we have to solve for the mean of all the means and the standard deviation of all the means. So again, the formula the mean of all the means is equal to the population mean, which is equal to 10.5. Then the standard deviation is equal to the standard deviation over the square root of n. And the standard deviation given is 3.6 over square root of n is the sample size, that is 16. So compute this. 3.6 over square root of 16 is 4. What is 3.6 divided by 4? Wait, you have two different answers. Which one is correct? It looks like William has, because 0.90%, 3.6 is very close to 4. So that is going to be 0.9. Okay. Any questions? All right, so that is equal to 0.9. Next is a sampling distribution for a sample of size 3. So earlier I showed you that these tables here, the columns here, are from here all the sample means of all those samples. And if you get all these means here, so we will be able to get the sampling distribution of all the means. So let's say a 1.0, how many 1.0 do we have here? And there's only one, so that's why we have it here, 1 out of 64. This, sorry, there's a 0.016, that is 1 out of 64. And let's say 1.33, how many 1.33s do we have? 1, 2, 3. So there's only 3, so that's why 1.33, the probability is 3 out of 64, which is equal to 0.047, and so on and so forth. So if you get all this, that's the probability distribution, sampling distribution of all the means. So these are all the probabilities. Any questions? Are you sure? Okay. No questions. But don't worry, I'm not gonna ask you. I was waiting for some of you to ask how are we gonna get the other probabilities. So look at this. There are 64 means here. I'm not gonna ask you to. Don't worry, I'm not gonna ask you to count how many 2.67s do we have, or how many 3.33s do we have, or a 4.0, and then compute for the probability. That's gonna take you a while to complete your table, right? And again, like was said, don't worry, we're not gonna do that, because there's a way to do that, and that is by using a central limit theorem. But before that, with all these probabilities, just like what we did for other distributions, we will be able to graph this using a histogram. And you will see it's either skewed to the left, skewed to the right, or a normal curve. And if your size is great, n is equal to 30, it approximates a normal distribution. So in practice, a sample size of n greater than 30 is considered large enough. Okay, so I mentioned that to construct that table, we just need a central limit theorem. And this is very important if you need to copy this. Central limit theorem, let mean be the mean of the large n greater than 30, simple random sample from a population with a mean, mu, and a standard deviation. And with that, we just need to use these formulas, like what we did earlier. Mean of all the means is equal to the population mean, mu, and the standard deviation of all the means is equal to the standard deviation over the square root of n. So the central limit theorem applies for all populations. However, for symmetric populations, a smaller sample size may suffice. If the population itself is normal, the sample mean will be normal for any sample size. So meaning, even if for any problems, even if the sample size is less than 30, but it is stated in the problem that it is normal, then you will be able to use central limit theorem. Otherwise, you have to make sure that the sample size is at least 30. Okay, let's check this example here. Sample size 45 will be drawn from a population with a mean mu of 15 and standard deviation of 3.5, is it appropriate to use the normal distribution to find probabilities of all the means? What do you think? Let's go back. When can we use the central limit theorem? Let me with the mean of a large n greater than 30, simple random sample for a population with mean mu and standard deviation. Example 1 here, sample size of 45 will be drawn from a population with the given mean and standard deviation. Is it appropriate to use the normal distribution to find the probabilities of mean? What do you think? Yes, very good. Yes, because n is greater than 30. So that's the first thing you're going to check, the sample size. It must be greater than 30. Okay, very good. Okay, how about this? A sample size of 8 will be drawn from a normal population with a mean equals -6 and standard deviation 5. Is it appropriate to use the normal distribution to find probabilities for mean? Yes or no?
No.
But it says here though that it is drawn from a normal population. So remember I mentioned, even if it's less than 30, but if it's drawn from a normal population, or if it's stated on the problem that it is normal, then you will accept it and still use the central limit theorem. Okay? So don't forget that. Let's try another one. A sample size of 24 will be drawn from a population with a mean 35 and standard deviation 1.2. Is it appropriate to use a normal distribution to find probabilities for mean? Yes or no? All right, that's correct. So the sample size is less than 30, and it's not stated on the problem that is drawn from a normal population. So we cannot be certain that the mean has an approximately normal distribution. Okay. All right, next is use the central limit theorem to compute probabilities involving some sample means. Example 1. Recent data from the US Census indicates that the mean age of college students is 25 with a standard deviation of 9.5. A simple random sample of 125 is drawn. What is the probability that the sample mean age of the students is greater than 26 years? So again, for this, what is the probability? Meaning you have to use normal CDF. So remember I told you for chapter 7, if it's you need to find the area, the proportion, the probability, you have to use normal CDF. And when you use normal CDF, you always have lower, upper, mean, and standard deviation, right? And for central limit theorem, the mean is the mean of all the means, and standard deviation is the standard deviation of all the means. So remember, just to recall the formula, the mean of all the means is equal to the population mean, just like here. It's already given, which is 25, and the standard deviation of all the means is equal to the standard deviation over square root of n. So you have the standard deviation here, 9.5, and you have the sample size n of 125. So you need to compute this first. Okay, so do not just substitute 9.5 here. Okay, so get your calculators. So it should be normal CDF. Then, just like what we did for 7.1 and 7.2, it says here greater than 26. What is 26? Is it lower or upper? Yes, lower. Very good. So this is 26. So your upper is 999, and mean of all the means is 25, and standard deviation, remember the formula. I think you could just type it 9.5 over square root of 125. Close parenthesis and enter. So try that. What did you get? 0.1196. Okay. Did you get the same answer? I know Michael, Louise, and Jared get the same answer, 0.1196. And do you have any questions about this? Okay, very good. So, all right, if you notice here, they got 0.1197, but our answer earlier, that is correct. That's most accurate. The reason why is we computed our standard deviation. We entered this 9.5 over square root of 125. Here they rounded off when they divide these two numbers to 0.85. So what we did earlier, that is more accurate. Okay. Let's try another one here. Okay, so based on the data from the Hereford Cattle Society, the mean weight of a 1-year-old bull is 1135 pounds. So the mean is 1135 with a standard deviation of 97 pounds. Would it be unusual for the mean weight of 100 head of cattle to be less than 1100 pounds? So again, unusual, so we have to check if it's less than 5%, right? Would you like to try this first? 2 minutes. Less than 1100. What is lower? Yes. So meaning your upper is 1100. Now the mean is
1135.
1135. And standard deviation is
Would it be 97 over the square root of 100?
yes, very good. Try that. And what is your answer? Okay, so 0.000. If you use only 4 decimals, so 0002, or if you use that, that is also correct. Okay.
Can you explain? I for some reason I got 9.7. I'm not sure what I'm doing wrong.
9.7.
Yeah, I got the square root of 100 is 10, and then I did 97 divided by 10.
Did you enter negative 9999?
No, just for, oh, never mind. I thought we were computing what the standard deviation would be.
Oh, it's the whole thing.
Gotcha.
Michael, how did you get 1.54? Did you enter, make sure that it is negative 9999? Oh, the reason why you got 1.54 is, yeah, the e raised to negative 4. Yeah. Michael, so again, whenever we talk about area, proportion, or probability, it should be between, your answer should be between 0 and 1. And when you got something like that, 1.54, check the very end. For sure you have 1.54, 1727637 e negative 4. So that's why you have to move the decimal that's negative 4 to the left. 1, 2, 3, 4. So that's a 1, 2, 3, 1, 5, 4. Okay, Michael? Michael, did you get that?
I had forgot. I had even asked you about that before. I forgot to move the decimal
Yeah,
because when I
okay.
did it, I seen everybody. I seen a couple other people had the same answer as me. It's just theirs was a smaller number than mine. I was like, this didn't seem right, but I forgot to move the decimal.
Yes, so don't forget that. Or I will accept if your answer, let's say on quizzes and tests, let's say if your answer is like this, 1.54 17, and you wrote e negative 4. I will accept this.
That's so nice.
Okay, because this is understood that you have the exponent of negative 4. Okay.
All right, all right. Thank you.
What does it look like when it's a positive number again?
Move it to the right.
Got it. Thanks.
Okay, yeah. All right, so actually that's uh 7.3. So you learn how to construct sampling distribution of the sample mean, and the use it's actually the whole section is all about the central limit theorem. So it's and to use the central limit theorem, so make sure that you know how to get your n, and then your mean is still the same as the given population mean, so there's no problem with that. Common mistake here is when you use central limit theorem, some students forget the standard deviation to change it to standard deviation over square root of n. Remember from 7.2, you change this whatever the given standard deviation is, right? Here you're going to change it, but you also have to divide it by square root of n. Okay, so it's still the same normal CDF, but don't forget to change the standard deviation. And later, after we finish 7.4, I will tell you the differences between all the sections, 7.1, 7.2, 7.3, and 7.4, and when to use those sections, okay? But before 7.4, let's solve some problems. Oh, I have to. Okay, I need to go back to Connect Math. Seven point. Three. All right, number 21. Okay, how's your mileage? So the mean highway gas mileage of the 2017 Chevrolet Sonic to be 28 miles per gallon. And assume the standard deviation is 3 miles per gallon. A car rental company buys 60 of these cars. So you have here the mean of all, the mean is the standard deviation, and n is equal to 60. So letter A, what is the probability? Letter B, what is the probability? Letter C, would it be unusual? So meaning everything is solving for the probabilities. So everything is normal CDF. So for letter A, so normal CDF greater than 27.5. So what is 27.5? Is it lower or upper? It's lower. So 27.5, and upper is, let's say, 9999. Then the mean is 28, and standard deviation is 3 over square root of 60. So try that and let me know your answer. Yes, that's correct. 0.9016. Then letter B, so still normal CDF. Between 27 and 27.8. So whenever you have between, remember, you already have your lower and upper. So this is 27, then 27.8, same standard deviation, mean and mean. So 3 over square root of 60. So that is correct, 0.2979. And letter C, would it be unusual if the average mileage of the fleet were less than 27 miles per gallon? So less than is going to be your upper. So this is negative 9999, less than 27. And then your mean is 28, standard deviation 3 over square root of 60. So you got 0.0049, and your answer is yes. Very good. Any questions? Well, one more. Taxes. The IRS reports that the mean federal income tax paid in a recent year was $8,040. So it says here, this is the mean, 8,040. And assume that the standard deviation is 5,000. So you're going to use that. And IRS plans to draw a sample of 1,000 to study the effect of the new tax law. So let's check all the questions here. A, probability. B, probability. 48 percentile, meaning the area. Unusual, unusual. Everything is probabilities. By the way, 7.3, everything is going to be probabilities. So that's why we're all using normal CDFs here. Okay. So it's just every time for this chapter, you will only see either less than, greater than, or between of the two numbers, always. So like this one, less than, whenever you see less than, meaning that is your lower. Is it? No, sorry. What is 8,000?
The upper number?
The upper number. So this is 9999. So this is the upper number, 8,000, and your mean is 8,040, and standard deviation 5,000 over square root of 1,000. Very good. 0.4001. B, between 7,600 and 7,900. So that is your lower and upper. Or you already have answers. Right, and that is correct, 0.1853. Okay, I'll let you work on C, D, and E. Wait, this one is a different question. Sorry. P40, 48% now, meaning that is 40%. Sorry, this one is different. So when given the area, 40% or 0.40, so meaning we have to use inverse norm. Okay, so inverse norm, 48% now, so you just have to enter 0.40, and then the mean is the same. And standard deviation, you also have to use the same standard deviation. All right, that is correct. 7 999.9. Very good. Then letter D, try this, less than 7,500, just like letter A. So here, so we could just use letter A and change it to letter D. So this is less than 7,500. So we just use 7,500. And what is your answer? Louise, is that correct? So remember, when you use normal CDF and if you see greater than 1, check the very end. So 003 or 0032 or 00318. Okay, and of course the answer is a yes, less than 5%. Okay, how about letter E? Can you tell whether it would be unusual for an individual to pay a tax of less than 7,500? What's the difference between D and E?
Population versus individual.
Yes, very good. So here it's the same as less than 7,500, so that is your upper. So this negative 9,999. This is 7,500. You still have the same mean of 8,040. And since you're talking about the individual here, so this is just simply your standard deviation, because you can still use the same formula, 5,000 over square root of 1. The square root of 1 is 1, right? Or this is just simply use 5,000. This is like 7.2. So actually 7.2 is just always you're getting the proportion, the probability of when n is equal to 1. So you're talking about 7.2, you're talking about individual. But 7.3 and 7.4, you're using central limit theorem, meaning n should be greater than, it's not going to be 1. Okay? So try this, and what is your answer? You all got 0.4217. And definitely it is not unusual. Oh, Mary Kyla has a different answer. Which one is correct? Yeah, that is correct. All right, thank you. Any questions? 7.3. Any questions? No? Okay. All right, 7.4. This time, central limit theorem for proportions. So remember 7.3, central limit theorem for means, this time for proportions. And we have another two objectives here. Construct a sampling distribution for a sample proportion, and then use the central limit theorem to compute probabilities for sample proportions. So in a population, the proportion will have a certain characteristic is called the population proportion, and that is denoted by P. And to compute for the sample proportion, which is our P hat, is equal to X over N. So copy that if you need to remember P and P hat. Okay, just an example here. A computer retailer wants to estimate the proportion of people in her city who own laptop computers. She cannot survey everyone in the city, so she draws a sample of 100 people and surveys them. It turns out 35 out of 100 people in the sample owns laptops. So that's why you will be able to compute for the sample proportion, which is 35 over 100. Or 35%. Just like the idea about a sampling distribution of the means is the same thing for proportions. So let's say out of a big population, and if you want to get a sample out of a population, you will be able to get a sample proportion, just like what we did here. You have a sample of 100 and 35 out of 100, you got that sample proportion. So what if you have a different sample, and definitely you won't get exactly the same as the sample proportion here. Same with this group. So all of this will not have the same, or some of them will have the same, but not all this, you will have the same. So the probability distribution of all the proportions is called the sampling distribution of the P. So example, consider tossing a fair coin 5 times. These produces a sample size n is equal to 5, where each item in the sample is either head or a tail. The proportion of times the coin lands on heads is a sample proportion P hat. The probability that it lands heads each time is 50% or 0.5. Therefore, the population proportion of heads is 0.5. Now, we look at all the 32 possible samples that can be constructed. 32 because when you toss a coin, either heads or tail, and you do it 5 times, so meaning 2 raised to 5, 2 times 2 times 2 times 2 is equal to 32. And those possibilities, when you toss it 5 times, are these. It's possible for you to have 5 tails, 4 tails and head. These are all 4 tails and head, or 3 tails and 2 heads, up to 4 heads and a tail, and all 5 heads. So these are all the possibilities. So that's why if you count all of this, that is equal to 32. And what is the proportion that you're going to get heads? So that's right, this one. If all the tosses you get tails, so that's why it's 0. If you get all heads, you're going to get 100% or a 1.0. And these are all the proportions. So this is very similar to what we did earlier. Instead of getting the means, this time you're getting all the proportions. Okay, and same concept also. If you get the mean of all the proportions, what do you think is the answer? Remember earlier, the mean of all the means is equal to the population mean. So if I ask you to get the mean of all these means, the mean of all these proportions, what do you think is the answer?
0.5.
Which is equal to, yeah, it's going to be equal to 0.5, which is equal to your population proportion. Okay, just like this. If you want to get the mean of all the means, it's just going to be the population mean. So if you do the same thing here, the mean of all the sample proportions is equal to your population proportion, P. So that's why I take note of this formula. And this time, your standard deviation is equal to the square root of P times 1 minus P over N. So copy these two formulas for mean and standard deviation. All right, let's try some examples here. The soft drink cups at a certain fast food restaurant have tickets attached to them. Customers peel off the tickets to see whether they win a prize. The proportion of tickets that are winners is P equals 0.25. So given P here, a total of N, the sample is equal to 70 people who purchase soft drinks between noon and 1 p.m. So let P hat be the proportion that win a prize. Find the mean and standard deviation of P hat. So mean is equal to the population proportion, which is equal to 0.25. Standard deviation of all the p hats is equal to the square root of p times 1 minus p over n. So that is p is 0.25, 1 minus 0.25 is 0.75 over n is 70. Compute that. All right, thank you. 0.0518. Okay, so don't forget how how to compute for your mean and standard deviation of all the p hats, because we're going to use this for central limit theorem. Okay, so remember earlier for the means, you should have to make it normal, you should have at least 30 as your sample size. Here you have to check that your n times p and n times 1 minus p should be at least 10. So the one at the bottom here, n times p and n times 1 minus p are both at least 10. Or simply this one. So if np is greater or equal to 10 and n is less, n times 1 minus p is greater or equal to 10, then the distribution is approximately normal. Otherwise, if it's stated in a problem, then it is okay. Then you will be able to use central limit theorem and use the formulas for the means of all the p hats is equal to p and the standard deviation of all the p hats squared of p times 1 minus p over n. Okay, so don't forget, you have to check first. Earlier, we checked each problem if n is greater than 30. So for proportions, we have to check np and n times 1 minus p should be greater than or equal to 10. Okay, let's check this. A sample size of 20 is drawn from a population with a population proportion of 0.7. Is it appropriate to use the normal distribution to find probabilities for p hat? So you have to check np should be at least 10. So what is n 20 times 0.7? 20 times 0.7 is 14, and it is greater than 10. How about n times 1 minus p? Again, it should be greater than or equal to 10, or at least 10. So 20 times 1 minus p, 1 minus 0.7 is 0.30, and 20 times 0.30 is 6. And this is not at least 10. So that's why the answer is no. Okay. Also here, let's see, if you compute for the first one, let's say 14, since your n is equal to 20, you could just subtract this from your n, and that's going to be definitely the answer of the other. 20 minus 14 is 6. Okay, let's check the next one. A sample of size 55 is drawn with a population proportion of 0.8. Is it appropriate to use the normal distribution to find probabilities of p hat? So n times p, 55 times 0.8 So this is a yes. Or the other one, you just 55, so 55 minus 44 is equal to 11. So that is also at least 10, right? So that's why the answer is yes, 44 and 11. Okay. All right, so next is let's use central limit theorem to compute probabilities. Example 1, according to Harris Paul, chocolate is a favorite ice cream flavor for 27% of Americans. If a sample of 100 Americans is taken, what is the probability that a sample proportion of those who prefer chocolate is greater than 30%? So sample of 100, and 27% of Americans, meaning that is your population proportion, P, and you want to get the probability, meaning that's normal CDF, greater than 0.30. So greater than 0.30 is if it's greater than 0.30 is lower or upper? Greater than, lower. So this 0.30. So upper is, let's say 9999. Then P is equal to, remember the mean of P hat is equal to P, and your P is 0.27. And the standard deviation is square root of P times 1 minus P over N. So it's up to you. You could use here, could type that square root of P, which is 0.27 times 1 minus P is 0.73 over N, which is 100. And you will get the answer. What did you get? Yes, that is correct. 0.2496. Make sure that when I ask you to try this because it's a practice on how to use your calculator. Questions? All right. Also take note of this. With this example, the very first thing that you need to check is the sample size. Sample size is 100. If it's greater than 1, then use the central limit theorem, either 7.3 or 7.4. And after you check that, if it's not stated, meaning your n is equal to 1, then you just have to use 7.2, meaning just the normal lower, upper, mean, and standard deviation. Again, if it's n is greater than 1, then you have to use central limit theorem. And also, it will be stated in the problem if you're talking about sample means or sample proportion. Sample mean is 7.3, sample proportion 7.4. Okay, so that's how you check each problem, so that you know which formula you're going to use. So like this one, approximately 60% of eligible voters voted in the 2016 US presidential election. I hope more next month. If a sample of 88 eligible voters were polled, so 88, so that's the first thing you check. So this is n is 88, so definitely you have to use central limit theorem. And here would it be unusual if less than half of them had voted? So you're talking about percentage here, proportion, so definitely that is your p. And with n is equal to 88, so definitely this is 7.4, since you are talking about proportion. So again, this is going to be normal CDF. And unusual, so meaning if you check if it's less than 5%, half of them, less than half of them. So what is your upper, lower and upper here?
Is the lower negative 9999 and the upper 44? Since it's half of them?
Half? No.
Oh, then it's just 88. Sorry.
No.
Okay, never mind.
Try again. Half.
44?
No, no. 50%.
Oh, I thought the half of them was referring to the sample for some reason.
No, no. Okay. And then your mean of all the proportions is 60%, and your standard deviation is square root of 0.6 times 1 minus 0.6 is 0.4 over n 88.
What is our Q again if it's going to be 7.3 versus 7.4?
7.4 is you talk about proportions.
Okay.
And then 7.3 is all about the means.
Okay, so if it gives us a percent, that's our Q for proportion.
Okay, so it's either a percent or okay, let's finish this first, and then I will show you when we go back to the previous problem.
Okay.
Yeah. So what's the answer here? Is it 0.0278? And Would it be unusual? Yes. Okay, any questions? I guess no questions. All right, so yeah, so here you see percentage here. Whenever you see percentage, one thing that is yes, Thelma. Whenever you see unusual, meaning you always compare it to 5% all the time. It should
I
be
have a
it should if it's less than 5% or 0.05, then it is unusual.
I
Okay.
also have a question.
Yeah.
So when it says like half of it, we basically have to consider that half of it, like it would be 100%. So that's where you got the 0.50 from
Yes.
on the last
Half of
question.
the population is 50%. Just like the previous example here, the question is what is the probability that is greater than 30%? This time it's given the percentage, 30%.
Okay.
Okay. Not this one, given greater than 30%. So that's why here, don't use this or don't use the half of this. Half of meaning that is 50%.
Got it. Thank you.
Okay. Yeah. Let's say if the question is, would it be unusual if less than a quarter of them had voted? So a quarter meaning you have to use 25%. Okay, so don't compute for a quarter of 88 or because you're gonna get a whole number here, right? And this is about proportion. If it's about proportion, your lower and upper is also gonna be like a percentage in decimals. Okay. So yeah, Chelsea's question about how to check if it's 7.2 or 7.4. 7.4, you will, the first thing is whenever you see percentage, automatic that is 7.4. And would it be unusual if less than half of them, meaning 50%, so that is proportion. So here also, look at the question, what is the probability that a sample proportion, if you see this, meaning that is 7.4. If you see from the question, what is the probability that the sample mean, meaning that is from 7.3. Okay.
Got it. Thank you.
So that is 7.4, and that is chapter 7. And let's answer some problems from the book. And look at this also. If this is from 7.3, right? And look at the questions here. All the questions. What is the probability that the sample? What is the probability that the sample mean? What is the probability that the sample mean? Sample mean, sample mean, meaning that is 7.3. You don't see percentages here also, so meaning that is sample 7.3. Okay, so that's the hint to use 7.3. And of course, don't forget that you should have, remember I told you, check the sample size n. it should be greater than 1. Because if your n is individual, meaning if your n is equal to 1 here, then this is 7.2. You don't need to use the formulas for the mean and standard deviation. Okay? So let's try 7. Oh, I need to log in again to Connect Math. So again, that is the whole chapter 7. So you should be able to complete the homework assignments for chapter 7, and make sure to do that tonight or tomorrow instead of waiting this Sunday, because those are practice problems for your quiz on Wednesday. All right, 19, government workers. So the Bureau of Labor Statistics reported that 16% of US non-farm workers are government employees. A random sample of 50 workers is drawn. So based on that statement, you already have a sample of 50, and it's equal to 50. So meaning you have to use a central limit theorem here, and you have a reported population proportion of 16%. So that's why definitely this is 7.4. Now letter A, is it appropriate to use the normal approximation to find the probability that less than 20% of the individuals in the sample are government employees? If so, find the probability. If not, explain why not. Is it appropriate? What do we need to use here to find out if it's appropriate or not? What do we need to do here? If the question is it appropriate? So what do we, yes, NP and N times 1 minus P. So NP, 50 times 16% is equal to 8. And 8 is, you can stop here since it's already less than 10. So the answer is no. Okay. All right, B. A new sample of 90 workers is chosen. And you can check this 90 times 0.16. What is 90 times 0.16? $14.4, that is greater than 10. And 90 minus 14 is also greater than 10. So definitely you'll be able to use normal CDF here, or the central limit theorem. So normal CDF, find the probability that more than 20%. So 0.20 is what is 0.20? Lower 0.20 and upper, so let's say 9999, and then the mean of all the proportions is 0.16, and square root of 0.16 times 1 minus 0.16 is 0.84 over n, which is 90. Point 1503. Thank you. The next, letter C, find the probability that the proportion of workers in a sample of 90 who are government employees is between 0.5 and 0.18. So again, it's normal CDF. So you already have the lower and the upper. And you have the mean and the standard deviation. You're fast. 0.2997. That is correct. Letter D. Less than 25%. So negative 9999, less than 25%. Then you have the same mean and standard deviation here. 0.16, 0.84 over 90. And your answer? Yes, very good. 9901. And last one, letter E. Would it be unusual if the proportion of government employees in a sample of 90 was greater than 0.25? So this is just like letter B. So greater than, so 0.259999, 0.16, and the square root of 0.16 and 0.84 over 90. And your answer, 0.0099. And it is less than 0.05, so it is a yes. Any questions? So the rest of the problem is just similar to all of this. So if you check those, so just don't forget always. Let me stop this. Oops. So just to review chapter 7, 7.1 is the standard normal curve. So it's either you use normal CDF or inverse norm. Normal CDF, make sure that you know your lower and upper. And then this one, the standard normal curve, is the default of your calculator. The mean is 0 and the standard deviation is 1. That is 7.1. If there's no given mean and standard deviation, it's understood that, that you're going to use the default of 0 and 1. Okay. Same thing with inverse norm. So remember, this is area, and then the standard deviation, mean 0 and standard deviation 1. Then 7.2 is the same thing, but the difference is this given. This time, you will see a given mean and standard deviation. So whatever is a given and the standard deviation. Seven point 3 and 7.4, this time you use a central limit theorem, CLT. And you're also going to use normal CDF. So I told you, that's why this is one of my favorite chapters. So you just have to use normal CDF and inverse norm. So lower, upper, and here you need to get the mean of all the means, and here the standard deviation of all the means. And here you need to get the mean of all the proportions and the standard deviation of all the proportions. Okay, and also if you use inverse norm for 7.3, so you're going to use the same mean and standard deviation. Any questions? So like what I said, don't forget here definitely for central limit theorem, n is greater than 1, and you would check that at least 30 or at least stated on the problem. Okay, and here 7.1, 7.2, you just talk about the individual when n is equal to 1. So please practice your homework assignments. You will see those type of problems on Wednesday.